An Introduction to Set Theory and to Philosophy and Methodology of Mathematics and Computer Programming by Jan Plaza. Section 1.4 Abstract Objects and Expressions, an overview. Let me start from an example which might be a little puzzling. The set containing 1 and 2 is equal to the set containing 2 and 1. Also, the set containing 1 and 1 is equal to the set containing 1. And perhaps the most controversial example, the set containing 4 over 6 equals to the set containing 2 over 3. To understand these equalities, of course we need to think about the axiom of extensionality, but also we need to make a distinction between mathematical expressions and abstract objects. The idea is that a mathematical expression denotes an abstract mathematical object. So we have expressions and objects. An expression denotes an object. To explain the third part of our example, 4 over 6 and 2 over 3 are fractions. This means they are symbols which we write on paper or on the board. They're contrasted with the rational number. That rational number could be written either as 4 over 6 or 2 over 3 and in many other ways, and whichever way we write it, it is the same rational number. The expressions are not the same, but they denote the same rational number. Whenever I discuss expressions, I will put them in quotes. On the other hand, when I want to refer to the mathematical object denoted by an expression, I do not use quotes. So here is another note we can make. 4 over 6 is a fraction, which is an expression that denotes the rational number 2/3. So analyzing 3, the set on the left contains one rational number. The set on the right contains one rational number. In both cases, the number is the same. Whether we use the expression 4/6 or 2/3, they denote the same rational number. Now let's look at part 2 of the example. This notation is an expression denoting a set. So is this. What mathematical object is denoted by the set on the left. A set containing 1. Also, the expression on the right denotes the set containing 1. By extensionality, the two sets are equal. Similarly, the notation used in the first part of the example in both cases denotes the same set. Let me give you one more example of expressions and mathematical objects. An example not directly related to set theory. In mathematics, we discuss sometimes so-called formal polynomials. And these are expressions. To give an example, 2x squared plus x plus 2 minus x squared minus 4x. This expression is a formal polynomial. Also, 1x squared minus 3x plus 2 is a formal polynomial. The two expressions are obviously different. They look different, they are of different length, they have different symbols in them. But it turns out that in this case, they both denote the same polynomial function. If you rearrange the terms and simplify, you will see that you come up with the same polynomial function. The distinction between expressions and objects, with expressions denoting objects, can be loosely compared to a situation common in computer programming. Namely, it is common to have two different variables in a program that refer to the same object in the memory of the computer. And it's very much like having two different expressions which denote the same object. Let me make a few comments on canonical forms. While many different expressions can denote the same object, it might be convenient to choose one of these expressions and call it a canonical form. So a canonical form of an expression denoting a particular object is one chosen expression denoting this object. For instance, there can be many fractions denoting the same rational number. -4 divided by 6, 2 divided by -3, -2 divided by 3. All these fractions denote the same number. We can choose this one as a canonical form. In general, by canonical form of a fraction, we will understand a fraction that is in simple terms and where the denominator is positive. The importance of canonical forms stems from the fact that they make it easy to tell if two expressions denote the same object. Given two expressions, convert them to the canonical form. If in both cases you obtain the same canonical form, completely identical expression, then you know that the original expressions denoted the same mathematical object. Maybe one more comment on this topic. When we write mathematics, we use expressions. We do not have any ability to present abstract mathematical objects. And we put the equals sign between two expressions. To mean that they denote the same object.